Alright class, so this is the last theorem I've got for you. It's the divergence theorem. Here's what it says. So E is a simple solid region, and S is the boundary surface of E. In other words, S is a closed surface. It's got a top, bottom, sides, and all. S is going to have outward orientation, and if F is a vector field whose components have continuous partial derivatives on an open region that contains E, then the surface integral of F with respect to the surface is going to be equal to the triple integral over the region E of the divergence of the vector field. And at least one of the physical sort of applications of this, there's a, I think it's called Gauss's law in physics. It says the charge on a surface is the same as the charge throughout the whole thing. So like the charge on the surface of a sphere would be the same as the charge or the divergence of the entire sphere. Okay, so that's what it says. That's pretty simple. So let's do an example. So here's our first example. We're going to find the flux of the vector field F, which is, let's say it's ZYX, over the unit sphere. X squared plus Y squared plus Z squared equals 1. Okay, so this is the question that we're going to do. And so that means normally we're asking to do this, so we're going to do this. This is unlike Stokes' theorem, this is just a one direction only. You would just take a surface integral and make it over a vector field and make it into a triple integral. Alright, so we got to calculate the divergence, and then we'll think about it's the unit sphere, so that should be pretty simple. So the divergence of F, remember this is the partial with respect to X, partial with respect to Y, partial with respect to Z, dotted with the vector field, which is Z, Y, X. Okay, so this is pretty straightforward. Derivative with respect to X of Z is 0. Derivative with respect to Y of Y is 1. And the derivative with respect to Z of X is 0. So this is 0 plus 1 plus 0. So that's pretty simple. That's just 1. Okay, so we're over the sphere. Okay, so this would be the rectangular version of it, and we're not even going to write what the bounds would be in rectangular. We're going to convert this to spherical. Okay, so it'd be the triple integral of 1 with respect to volume. So we're just going to convert this to spherical. We'd have to change the integrating factor as rho squared sine phi, and this would be d rho, d phi, d theta. Okay, and we're not even going to bother integrating that because that's just the volume of the sphere. So that's going to be 4 pi over 3, and that's it. Because the radius is 1. Okay, let's do another example. So example 2. So let's do one that's a little bit more interesting. So we're going to evaluate the flux integral f dot ds where S is the region bounded by, okay, it's going to have several different parts. So what do we got here? We got Z equals 1 minus x squared. That's a cylindrical sheet. Okay, y equals 0. That's a plane. Z equals 0. That's a plane. And y plus z equals 2. Somebody's texting me. I should have turned that off. And let's say I take the vector field too. F is xy y squared plus e to the xz squared, and then sine of xy. Okay, if you remember the fundamental theorem for line integrals, this is sort of similar in nature, because we're going to find, and also we did curl when we were doing the Stokes theorem, and you saw that sometimes when you do curl for something, it just simplifies it. So that's what's going to happen here. The divergence of this thing, you got these crazy parts like sine of xy and e to the xz squared, but when we do the divergence, those are going to go away. And of course the surface should be outwardly oriented. I didn't write that down, but that would be part of the description. Let's draw the surface. So I've got a cylindrical sheet sort of going like this, and then I've got this plane that should be, you know, if I'm thinking about solving for z here, that would be z equals 2 minus y. So that would be this plane that sort of cuts like this. So let's see if we can give this guy a good shape. That would be sort of what that region looks like. Okay. So noticing this, it would be the easiest to go dy first. Okay, when we get to the triple integral. All right. So the divergence of f, oops, forgot the v. Okay, so as we saw last time, it's del dotted with f. So it's the derivative with respect to x of xy, which is y. Oops, sorry, it's not a vector. Y, and the divergence of y squared plus e to the xz with respect to y, so that goes away, and that's going to be plus 2y. And the divergence, the derivative with respect to z of sine of xy, and that's going to be 0. So the divergence is going to be 3y. So I got my integral, I got my picture of the region. So triple integral. So y would go 0 to that plane. So 2 minus z. And there's a siren going outside too. Then we're in the xz plane. In the xz plane, you're just dealing with a parabola pointed down. So that would be your z, and this would be your x. So the easiest thing to do would be to do dz next. So we've already done dy. dz would go 0 to the parabola. So 0 to 1 minus x squared. And then x is going to be minus 1 to 1. Okay? And let me say dx here. That would be it. I'm not going to, once again, I'm not going to evaluate this one. I'll let you guys do it. But that's how you use the divergence theorem. The divergence theorem is pretty nice. Like I say, it's only one direction, so you don't have to worry about, do you do this or do you do that? And it's a triple integral, so as long as you can set up a triple integral, it's pretty straightforward. Okie doke. That's it.